Great. So I'm going to be looking at mechanisms for agents with nonlinear utility, but let's start with linear utility. So linear utility agent is an agent whose utility is given by some value for allocating, receiving a resource, minus the price that's they're asked to pay for that resource. One of the canonical models of nonlinear utility is given by agents with budgets. Okay, and so the issue of agents with budgets is that if the price they're asked to pay is too high, then they are not willing to pay that, and so this introduces a nonlinearity to the utility function. And so the simplest model of agents with budgets is their utility is linear as long as the payment they have to make is less than the budget, and it's minus infinity otherwise. So to give an example result that I'm going to be talking about later in this lecture, we're going to be looking at reductions of from lifting results for agents with linear utility to apply to agents with nonlinear utility, essentially showing that a lot of the conclusions that we've learned from studying the much simpler situation of linear utility agents, these conclusions approximately are true under more general nonlinear utility models. In other words, these are sort of robust conclusions. And so one such result is for linear utility agents in multi-unit settings and revenue maximization is the objective. Sequentially posting prices gives you an E over E minus 1, which is about 1.58, approximation to the revenue optimal mechanism. And what we're able to show is that if I look at the sort of analogous scenario, but with nonlinear utility, and this is, I'll look at the setting of independent private budgets, that this this approximation factor gets worse by only a factor of 3. And so you end up with a 4.78 approximation. This linear utility result is actually true. It's due to a really nice paper by Chichian. And so since this is a reduction, it means that our private budget utility result is also true. Great. So that's a sort of a high level where we're going. I want to start out by talking a little bit about why we want to go there. So the goal here is to try to develop an economic theory for complex environments. And the challenge of trying to develop economic theory for complex environments is that, well, if you plug into the classical microeconomic analyses, you're going to get a complex answer, or you're going to get no answer because it's not going to be tractable. And so what we're going to be trying to do instead is extend understanding that we've been able to glean from simple models to more complex models using ideas of approximation. Okay, and so we're going to be invoking what I call the method of approximation. Okay, and that is trying to understand the world using the toolkit of approximation. And so, for example, we're going to be asking whether results for simple models approximately hold in richer models. And if the answer is yes, then this is great, because it means the simple model approximately captures the rich model. And the extra details that we threw into the model to make it rich actually don't matter that much for understanding what's going on. On the other hand, if the answer is no, if the results from the simple model don't approximately hold in the richer model, it means that actually we need to dig in and really understand what's going on here. We're gonna have to really take take the richness of the model carefully, because if we don't, the conclusions we have are far from good. So I want to talk about some prior work on this agenda for linear agents. So again, these are actually single-dimensional linear agents. I'm selling units. The agents each want a unit, and they have a single-dimensional value for getting a unit, and they have linear utility value if they win minus price. And so there are a lot of interesting results from the literature. This is the most studied problem in mechanism design, is a single-dimensional linear case. It's the most studied problem. And so there are a number of really amazing results helping us understand this problem. Some of my favorites are, first, that pricing-based mechanisms are in fact revenue optimal. And this, you can see the details of by looking at the virtual value analysis of Myerson or the marginal revenue interpretation of Bulow and Roberts. Another nice result is that the one I quoted a second ago by Chi-Chi Yan, showing that sequential posted pricings are approximately optimal. Okay, so I could come up with the optimal pricing-based mechanism, but maybe it's complicated. And I just want to do some simple price posting. Actually, that's guaranteed to get most of my revenue. Another result is that if you're selling a single item and the agent's value distributions are non-identical but satisfy a natural concavity property, then just posting an anonymous price. Just post a price, and one of the buyers will show up if they want to buy they'll buy it at that price. Otherwise, no one buys it. Just such an anonymous pricing mechanism is approximately optimal. And so what I want to point out is that for our method of approximation, these second two results tell us something interesting about the world. So sequential pricings. We post a price, the agents show up in some order and take it or leave their prices. Note that competition is not driving revenue in these settings. Okay, so in some sense, competition is not all that important because I can get good mechanisms without competition. Also, the revenue optimal auction here has to have all the bidders present at once. But this sequential pricing doesn't. It just sort of posts the price to agents as they show up, then the agents leave. So simultaneity is not important. One of my favorite examples of this is the eBay auction, or the eBay mechanism. So, eBay, rather than having everybody show up in a room at once and run an auction, they let people show up over time. And having everyone together at once is actually not all that important for getting good revenue. On our third result, the fact that anonymous pricing is close to optimal, it means that discrimination is not that important. And maybe we don't like discrimination anyway, but maybe we would discriminate if it could get us much more revenue than we could with a non-discriminatory mechanism. And what this says is actually you can't get that much more revenue with a non-discriminatory mechanism. And so, one of the conclusions I like for this is trying to model these extra details of the environment, such as collusion or asynchrony or non-identicalness of the players. So you might want to discriminate. This is actually not all that important. We learn, most of what we needed to learn by studying really simple environments where all the bidders show up at once and they're identical and auction theory is easy. So what we're doing in this paper is we're showing that these results can automatically be lifted and applied to nonlinear agents as well. So if I have approximation results that I've shown for for linear agents, then for large families of agents with nonlinear preferences, those approximation results approximately extend to nonlinear preferences. Meaning, in some sense, nonlinearity is not that important. And this is sort of, I think, really quite helpful because nonlinearity, as we'll see shortly, is one of those areas of mechanism design where optimal mechanisms are really not understood by economic theory. This is sort of in the challenging environment where I said, I said in my first second line on the slide that microeconomic analysis give complex answers, if any. Here mostly you don't get any answer for nonlinear mechanism design. And yet we're saying that essentially nonlinearity is a detail. We sort of learn enough about what makes mechanisms good just by studying linear agents. And one reason why I'm sort of excited to talk about this work at a summer school is that the structure of the kind of result we're showing here, I think, is very powerful. And it's very useful to think about things in those terms. And so what we did here is we wrote a meta-theorem. This meta-theorem says, if you have theorems about approximation for linear agents that use the fact that the mechanisms for linear agents are pricing based, then you can automatically extend those theorems to nonlinear agents. And so, we wrote one, meta-theorem, but this meta-theorem then implies many, many different results. Because you can take it and apply it to all of your favorite, many of your favorite results for linear agents and get automatically a result for nonlinear agents. So I really like this kind of meta-theorem. And it tells you some of the power of theoretical approaches to mechanism design economics, is that you can, very quickly say things about many, many environments, which is especially nice. Cool. So this is a sort of illustration of what I think we're doing when we do economic theory. This is some illustrations that Pablo Picasso did over a period of about a month in 1945, where he's looking to distill the essence of what it means to be a bull. And so he starts drawing these very detailed sketches at the top, and he ends up with really understanding what it means to be a bull with his last sketch in the bottom right. And I think that the role of economic theory really is not to get all the details right. The role of economic theory is to understand the bird's eye view of sort of what's important. Great. So I've got a slide with a bunch of related work, which I'm basically not going to talk about, but the slides will be shared with you, and so you're welcome to sort of look back on this. There's been a lot of really great sort of heroic work on mechanism design for nonlinear agents, and this is this is hard stuff. And it's hard stuff, but they get results in sort of very simple environments. So typically IID environments, typically with a lot of assumptions on the scenario that make it sort of nice and some kind of get vexity properties, for example. And these are typically for and so if you want to like generalize these to asymmetric environments beyond this, you end up doing this really difficult stuff of optimizing over reduced forms, which was pioneered by Border. And there was some recent work in computer science looking at computational methods for optimizing over reduced forms. And so while this ends up giving you computationally tractable mechanisms, it doesn't give that much understanding of what's going on. Just being able to give a polynomial time algorithm for something doesn't mean that we understood it. And so then there's a lot of work in approximation, which is following this agenda that I mentioned of sort of the method of approximation. Many of it gives you, nice answers where you understand things. You understand sort of what are the drivers that make mechanisms good in these environments with nonlinear agents. And so what we're going to do today is basically try to lift results from nonlinear agents to the settings of approximation. Great. So what I'm going to do for the remainder of the lecture is I'm going to describe the basics of this meta theorem, this reduction that shows that if I have results for linear agents, I can lift that result and apply to nonlinear agents, assuming that the nonlinear agent problems satisfy a nice approximation property. And then in the third part of the talk, I'm going to talk about that single agent approximation property that we need to then lift these results from linear agents to nonlinear agents. Okay, so let's jump into sort of one of the canonical models of nonlinearity, which is this independent private budgets model. Okay, so imagine you've got n agents and you have m units of a single item. This is the multi-unit setting. And the agents will have values. VI will be the value of agent I, and they'll have budgets. BI will be the budget of agent I. And we'll assume, we're going to be doing Bayesian mechanism design. So we'll assume that these values are drawn from a distribution F, and these budgets are drawn from distribution G. And we're going to assume that everything is independent. So the values, the agents are independent of each other, and each agent's value is independent of their budget. We'll assume we have a feasibility constraint. The one I've given here is that I have m units of a single item to sell, but the results are going to be applying to general feasibility constraints. And we're going to require that our allocation, it could be a randomized allocation. So for example, for multi-unit auctions, to be feasible, if I have m units to sell, it better be that the sum of the probabilities I sell to each of the agents, the sum of the xi's, is at most m. So that'd be an example of a feasibility constraint. Okay, and we're going to have payments, and we have nonlinear utility. So an agent has linear utility up to their budget, and if they are asked to pay more than their budget, they have minus infinity, a negative utility. All right, and what we're going to be doing is analyzing multi-agent mechanisms by looking at what happens for single-agent mechanism design problems. And so when I'm looking at a single-agent mechanism design problem, I'm going to drop my subscripts. Okay, so if I've just got one agent, then X is going to be the probability I allocate to that agent, and P is going to be their payment, and B is going to be their budget. Cool. Okay, so I said previously that optimal mechanisms for agents with budgets are complex. So for this problem I just put down on the previous slide, the optimal mechanism there is complex. There's a general approach for solving these. You project ex post feasibility onto the interim reduced form, and then you optimize revenue across your agents, the sum of the payments the agents make, subject to this interim feasibility. And then you optimize each agent's individual revenue subject to the interim allocation rule that comes from this interim feasibility. And the result of this sort of two-stage optimization where you optimize individual revenue for each agent subject to the fact that what you're doing for each agent jointly together is feasible is in fact optimal. And if that seemed complicated to you, indeed it is. And so we're not going to be doing that in this talk. We're going to be trying to show approximation results. We're going to be trying to come up with simple mechanisms that approximate this optimal complicated mechanism. And the first thing that's going to be a challenge if you're trying to approximate something complicated is that, well, it's complicated and so you don't understand it. And so if I want to use, come up with theorems to show that something simple is good compared to it, I have to have some understanding of it. And a canonical way to come up with these approximation theorems is to identify an upper bound that we do understand. And one of the most tried and true ways of coming up with an upper bound that you do understand is to relax some of the constraints of the problem to make the problem a lot easier. And so the idea is, let's relax the ex post constraint on feasibility. Okay, so an ex post constraint on feasibility says, well, if you had M items to sell, you better not sell M plus 1 items because you don't have that many. So that would be infeasible to do it. Okay, so ex post feasibility says no matter what you do, no matter who shows up in your auction, you can't sell more than the number of items you have. And the idea of ex ante relaxation is to relax this ex post feasibility so that it holds an expectation. Okay, so if I have M items to sell ex post, I'm going to relax that to sell M items in expectation, okay, on average. Okay, and the thing about selling M items in expectation, well, it's okay if I sell more than M items in some cases, as long as I sell less than M items in other cases, then it all balances out, and on average, it's not more than M. Okay, and it turns out that if I'm optimizing revenue in, if I'm optimizing sort of to ex ante feasibility, things become a lot easier, and they essentially decompose across the agents. And so this is going to be much easier to understand. We're going to be able to get a lot of mileage by understanding this this ex ante relaxation. Okay, and the theorem that I wrote down here is sort of the obvious theorem. Well, look, I had an optimization problem of coming up with an optimal mechanism subject to ex post feasibility. I relaxed some constraints. So the optimal solution to the relaxed problem can't be worse than the optimal solution to the original problem because the optimal solution to the original problem satisfies the constraints of the relaxed problem as well. So it was a valid solution. So the optimal solution to the relaxed problem is only better. The ex post infeasible mechanism that solves the ex ante relaxation problem is an upper bound on the optimal problem for the ex post feasible optimization question. Okay, and so remarkably though, this upper bound is not too loose. Okay, oftentimes this upper bound is actually a pretty close upper bound on the optimal thing. And so one example, and the multi-unit environment I had on the previous slide is a special case of matroid environments. So if you don't know what matroids are, don't worry about it. Just think about multi-unit or single item auctions. But in general, for matroid environments, E over E minus 1, which is about 1.58, times the revenue of the optimal mechanism actually is bigger than the ex ante relaxation. So what does this mean? You relax feasibility, you solve the ex ante feasible problem. That doesn't increase the revenue you could get by more than a 1.58 factor. Okay, so you're gonna potentially increase your revenue, but not by too much. And this is good because if I'm going to use this as an upper bound, the best I could do is to show my mechanisms are, optimal, and then they suffer this approximation factor anyway. So this sort of like E over E minus 1 is an upper bound on how good we're going to be able to show approximations using this approach. Great. I want to think about how we solve this ex ante relaxation problem. Okay, and so the first thing to understand when we want to solve this ex ante relaxation problem is what does ex ante feasibility mean? And so ex ante feasibility is just the following. A profile of allocation probabilities, which I'll denote by Q1 through Qn, is anti-feasible for a constraint if there is a distribution over feasible allocations such that the marginal allocation probabilities are equal to the given allocation probabilities. Okay, what are the marginal allocation probabilities? So I have a distribution over feasible outcomes. I look at the probability that agent I is served, that's Qi. Okay, I do that for all agents I. This is going to give me some profile of QIs. And we'll call that ex ante feasible because there's a distribution over ex post feasible outcomes that gives me this profile of marginal probabilities. Okay, so for example, if I have a single item, the ex ante feasibility of a single item is just that the sum of the allocation probabilities is at most 1. Okay, I have one item to sell. So it better be that in expectation, I sell at most 1 item, meaning the probability I sell to each agent is at most, sums to at most 1. Great. Okay, so I want to look at how I'm going to solve this ex ante relaxation problem. And to do that, I want to consider, well, imagine I'm selling to some particular agent with ex ante probability Q. What's the best thing to do? And so I'm just going to define the ex ante payoff curve for any single agent as the optimal revenue I can get from any mechanism that sells to that agent with ex ante probability Q. Okay, and now I can, using this single agent solution, I can tell you exactly what the ex ante relaxation program is. I want to, and I'll denote it by EAR, ex ante relaxation, and you're given these single agent revenue curves R and the feasibility constraint X, and we're going to maximize over allocation probabilities Q that are ex ante feasible of the sum of the optimal revenues that I get from selling to each agent with their corresponding ex ante allocation probability. So what you see here is that in essence, the optimization problem decomposes across the agents. Once you tell me the probability I sell to any agent, I know my best revenue. It's this given by the revenue curve. And by looking at the ex ante optimization problem, the revenue decomposes. Okay, and all I need to know to solve this problem is these revenue curves and the feasibility constraint, and I can tell you what this ex ante relaxation is. Great. So that's what happens if I run optimal mechanism, the optimal mechanism for a single agent. What happens if I restrict myself to post per unit prices? Okay, so on the previous slide, I said, R of Q is the revenue I get from the single agent optimal payoff that sells with some ex ante probability Q. And this could do some crazy thing by like offering lotteries or, doing something, something weird. What if I do something really simple? What if I just offer this agent a per unit price such that the probability that the agent buys when a random agent drops from the distribution, the probability that a random agent from the distribution buys is Q. Okay, and so what do I mean by a per unit price? Well, if the per unit price V hat is below the agent's value V, then an agent with value V and budget B is going to buy what? Well, they're not going to buy more than one because I only have one item to sell. So they're going to buy up to a unit 1. And if the per unit price is too high, then they're going to stop buying early because they're going to spend all their budget. Okay, so they're not going to buy more than 1 unit because that's the maximum probability I can sell to them. And they're not going to pay more than their budget. So if my price per unit price is V hat and their budget is B, the most they could buy is B divided by V hat. Okay, and so now I can define sequential posted pricing. Okay, so a sequential posted pricing is given these per unit pricing curves and the feasibility constraint. And what we're going to do is we're going to pick an order and per unit prices to offer all the agents. And what we're going to do is we're going to order the agents according to this order sigma, and we're going to offer them each, if it's feasible to serve the agent, I'm going to offer the agent the per unit price, and they're going to buy whatever they want to buy according to their price posting revenue curve, given the per unit price. Okay, and note that sequential posted pricing is well defined by the per unit pricing revenues and the feasibility constraint, which tells us how to basically run this, how to run this mechanism. Okay, so in general, this price posting revenue curve is not concave. It could be some arbitrary, it can't be arbitrary, but it generally it's not concave. And so we're going to be interested in the concave hull of it. And a nice theorem that follows from the literature on single dimensional linear agents is that the sequential posted pricing is an E over E minus 1 approximation to the ex ante relaxation. And this is the sequential posted pricing defined on the price posting revenue curves, and the ex ante relaxation defined on the concave hull of the price posting revenue curves. Okay, this follows from a standard result for linear agents where revenue curves are given by these quantities. Okay, and so for linear agents, in fact, the optimal revenue is given by the convex hull of the price posting revenue. And a corollary of that is that if the optimal revenue is given by the price posting revenue, then if you look at my equation, I can swap the ex ante relaxation revenue for the concave hull of the price posting revenue curve, P bar, with the revenue curve because they're equal. Okay, and so then I have the result that says that my sequential posted pricing mechanism is an E over E minus 1 approximation to the ex ante relaxation to the optimal revenue. And this is great because we know the ex ante relaxation is an upper bound on the optimal revenue of any mechanism. And so what we've just proven by this result is that sequential posted pricing is an upper bound on the optimal mechanism. Okay, so this is what happens for single dimensional linear agents. Okay, and so what I want to do on my next slide is I'm going to lift this result, or next couple of slides, is I'm going to lift this theorem. This is actually just a restatement of classic result in the literature due to Chi-Chi-Yan. I'm going to lift this result for linear agents to nonlinear agents. Okay, so for nonlinear agents, the concave hull of the price posting curve is not generally equal to the optimal revenue I can get. And this is sort of the main thing that makes nonlinear agents difficult to work with. Okay, so here's I want to define a closeness notion. Okay, I want to define a notion of when nonlinear agents behave sort of like linear agents when it comes to revenue curves. And so in particular, for nonlinear agents, as I said, the revenue curve and the concave hull of the price posting revenue curve are not equal, so they could look like this. I've drawn here with the red and the black curves. Okay, so we'll say that the nonlinear agent is zeta close to being linear if for every probability of allocating, every ex ante probability Q, there exists a smaller probability where I can get a zeta approximation. Okay, so pictorially, if we scale down the revenue curve, the ex ante revenue curve by a factor of zeta to get this dashed red line, and then we extend the price posting, the concave hull, the price posting revenue curve to the rightward, which allows us to choose smaller probabilities. Then what we're saying is this gray dashed line is above the red dashed line. Okay, that's the property that we need, is the gray dashed line is above the red dashed line for some constant zeta. Okay, so this is our notion of zeta closeness. It doesn't mean that the agent's preferences are approximately linear. It's that when we optimize single agent revenue via price posting, it approximates the optimal revenue I can get from all kinds of crazy mechanisms, not well beyond price posting mechanisms. Okay, and linear agents, these revenue curves are equal. Okay, that R and P bar are equal, so this trivially holds. Okay, and so this generally doesn't hold for nonlinear agents, and so this is the extent to which it doesn't hold. Okay, zeta closeness captures that extent to which it doesn't hold. Okay, and so our theorem is that if I have zeta close agents and I have a downward closed feasibility constraint, then if sequential posted pricing is a gamma approximation to the ex-ante relaxation, then sequential posted pricing is a zeta gamma approximation to the ex-ante relaxation for nonlinear agents. Okay, so in other words, if someone has proven a approximation result for sequential posted pricing for linear agents, and there are a number of these in the literature, then if we have zeta close agents that are nonlinear, we can automatically lift this result for linear agents, and it's going to hold for nonlinear agents, approximately. And the approximation factor we lose is just the zeta, the additional approximation factor we lose. So here's the proof. Okay, it's very simple. Okay, so first we're going to look at the ex-ante relaxation. Okay, and we're going to start with the ex-ante relaxation for the original environment running the optimal mechanisms. And the point is that if these agents are zeta close, that means I can take the solution to the ex-ante relaxation, and I can find allocation ex-ante probabilities that are still feasible by decreasing the allocation probability. And this is why we require downward closure, because it allows us to decrease the allocation probability to find ex-ante allocation probabilities where the revenue is a zeta fraction of the revenue from the original ex-ante program. Okay, so this is a straightforward argument to make. Okay, and then we just plug into the fact that that sequential posted pricing is a gamma approximation to the ex-ante relaxation on the between the price posting revenue curve and the concave hull of the price posting revenue curve. And this follows by the assumption for linear agents. Okay, so for linear agents, price posting revenue curves equal their convex hull. So this is exactly the approximation bound that you would need to show that such an approximation result held for linear agents. And then combining these two results, we have the desired approximation. So just substituting. Okay, so I wrote this proof for sequential posted pricing mechanisms, but this exact same proof approach applies to any linear agent result that's proven based, that can be described as a pricing-based mechanism. Okay, so I can essentially convert pricing-based mechanisms for linear agents into per unit pricing-based mechanisms for nonlinear agents, and then lift those approximation results to nonlinear agents. Great. So I showed you how to do the reduction, and I now need to instantiate the reduction. I need to show you that this zeta closeness property holds for interesting nonlinear agent problems. And I want to point that this is a single agent question. Given a single nonlinear agent, can I show that the ex-ante revenue curve and the price posting, the per unit pricing revenue curve are satisfied as zeta closeness definition? So let's remind you what that definition is. It says that I can find smaller allocation ex-ante allocation probabilities such that the concave hull of the price posting revenue curve is at least a zeta approximation to the revenue curve. Okay, so we in the paper we proved a number of zeta closeness results. Amazingly, in many settings of interest, zeta is 1. Okay, well, what is that? What does it mean for zeta to be 1? Well, it means you take an approximation result for linear agents, and you don't lose anything in extending that result to nonlinear agents. So the same bound holds. Okay, and why intuitively might it be that a nonlinear result you don't lose anything when you go to nonlinear agents? Well, here's the intuition. The intuition is when agents, for example, when agents have budgets, that actually means if you've heard of the term information rent, sort of the utility the agents can gain because they have the private information. Well, the budget actually lowers their information rent because it means the somehow their value, the fact that their value is private, is now less useful to them because their budget might get in the way. And so in a number of environments, this sort of intuition holds true. And you know, the results for linear agents just automatically apply to nonlinear with no reduction in the approximation factor. Okay, so we analyze 2 canonical objectives, revenue and welfare. We look at some classic environments for nonlinear preferences, like public budgets, like independent private budgets. And you know, one of them that I think is especially interesting here is endogenous values, which is not even an expected utility environment. So it doesn't satisfy. If you once you look at the problem in the typical way we look at it in the auction problems, it's not going to satisfy the von Neumann Morgenstern utility model. So this endogenous value setting is the setting where agents can pay some cost to invest to like increase their value, and then you want to design a good auction in this environment. There's also some results for risk-averse agents, which I didn't include on this slide. But many sort of the canonical environments for nonlinearity, we have zeta closeness results. So in the remainder of the talk, I want to go a little bit into how you prove these kinds of approximation results. And in the paper, we were actually able to leverage a lot of, you'll note that these are single agent analyses. And actually there's a lot of single agent analysis already in the literature. And so we were able to, you know, build upon a lot of the analysis already in the literature. Many of the results we had to strengthen because most of the literature didn't look at our question exactly. And so our question is showing that these ex-ante, these single agent ex-ante optimization problems are close, given some, you know, probability I can serve the agent, and that doesn't typically come up in the literature, and so we had to sort of add that to the problems. And so rather than show you our results, which are more complicated versions of what's in literature, I'm actually going to show you these really, you know, clean, simple to state, simple to prove results from the literature that really elegantly do main parts of our analyses. So the first thing I'm going to look at is posted pricing for unlimited demand agents. So we have a unit demand setting in our problem, and what happens if we look at unlimited demand? So the agents might want more than 1 unit. I'm then going to talk about classic results based on single sample mechanisms, and then a result that says that I can understand agents with private budget by looking at what would happen with agents with the public budgets equal to the expected value of the private budget. So these are some really elegant approximation results by other people that I think are, you know, especially like these are sort of staples of the literature. Cool, so I'll start with a result by Zoe Abrams. Posted pricing for unlimited demand. So let me remind you that we were originally considering a problem of unit demand. Okay, so for a unit demand agent, they're going to buy at most 1 unit because they're unit demand, and they're going to buy up to their budget if the price I post is below their value. Because this is the equation I gave before for how much they demand. Okay, so they demand the minimum of 1 unit, which is their unit demand. They don't want more than 1 unit, and B divided by V hat, the price, per unit price we post. So unlimited demand just gets rid of the constraint that we have 1 unit. They'll, look, if their value is, if the price is less than their value, they're going to buy up to their budget's worth of units. Okay, so here's the result by Zoe Abrams, is that unit demand agents are actually, it says too regular, it should say too close. Okay, unit demand agents are too close. Okay, so here's the proof. So I want to show that posting a price such that posting a price that sells with ex-ante probability Q hat. I want to show that that's a true approximation to the revenue optimal way to sell with ex-ante probability Q hat. So let's look at that price. So if I post a price that's, let's let V hat be this price. Okay, so in other words, if I sell with probability Q hat and I post a per unit price of Q hat, well, then what's my total revenue? Well, it's the per unit price times the quantity I sell, and the quantity I sell is Q hat, so it's Q hat times V hat. Great. Now let's consider the ex-ante optimal mechanism, which has revenue R of Q hat. And let's divide the contribution to the revenue into two pieces. Okay. So this ex-ante optimal mechanism is going to sell to some players potentially with a per unit price lower than V hat, and it's going to sell to some players potentially with a per unit price higher than V hat. Okay, so agents with a per unit price less than V hat, well, we only have Q hat units that we're selling. Okay, and we're selling to these agents with a per unit price less than V hat. So the most we can get from them is V hat Q hat, which is if we increase the per unit price that they were selling to them to V hat and sold all Q hat units that we have. Okay, but that's exactly equal to this posted pricing revenue. Great. Now let's look at agents with per unit price greater than V hat. Well, look, no agent pays us more than their budget. Okay, so in particular, these agents don't pay us more than their budget. But these agents are unlimited demand agents, and they had a per unit price greater than V hat, and they were buying. Which means when we post price V hat to them, they're going to spend their entire budget, which is what happens with limited demand agents. If we post a price V hat less than V, they spend their entire budget. Okay, so, well, if they spent their entire budget when we posted price V hat, they can't spend more than their budget in the optimal mechanism. So again, the contribution to the revenue of R of Q hat from these agents is at most the posted pricing revenue, P of Q hat. Okay, so for agents with price per unit price less than V hat, they pay at most this per unit price. For agents with per unit price greater than V hat, they pay at most the posted pricing revenue. And so combining these results, twice the posted pricing revenue is at least the ex-ante optimal revenue. Okay, great. Okay, the next staple analysis from the literature is the analysis of the single sample mechanism for linear agents. And the theorem, one way to state the theorem is the following. if I have a regular valued agent, and regular just means that their revenue curve, this R of Q hat is, or sorry, this P of Q hat is concave, then the revenue from posting a random sample from the distribution, the price equal to a random value from the distribution, is at least half the optimal revenue. That's what the theorem says. And so I want to draw a picture of what this is saying. Okay, so if I look at my revenue curve, R of Q hat, R of Q, okay, it's a concave function. That's what regularity gives you. And the revenue from posting a random price from the distribution is just the expected value of the revenue curve from a uniform random quantile, which is equal to the integral of the revenue curve, i.e. the area underneath the revenue curve. So the revenue from posting a random sample is the area given in blue in this picture. But if I was going to do the optimal thing, I would post a price that corresponds to the quantile that maximizes this revenue curve. So I would post the Q hat star that I've written and I've drawn on in the slide here. And the revenue here, I can interpret. The revenue here is obviously the height of the revenue curve at Q hat star. But because this plot goes from 0 to 1, I can also interpret this revenue as the area of the dashed rectangle. Right, so the optimal revenue is the area of the dashed rectangle, and the revenue from posting a random sample from the distribution is the area in blue underneath the revenue curve. And now we're just going to invoke the regularity, which is, again, the concavity of this revenue curve, to argue that the triangle, the inscribed triangle, is less than the blue area, the revenue from posting a random sample. And by simple geometry, the inscribed triangle is exactly half the rectangle, which is the optimal revenue. And so here we see from simple geometry that twice the expected value of a random quantile of the revenue curve is at least the optimal revenue that I can get from posting a price. Okay. Actually, let's. So I've now done the first two of my intended, fundamental results from the literature. I'm now going to jump into the last one. Okay, so the last result shows that if I'm trying to analyze agents with private budgets, that's going to be complicated. But I can get a bound on the best I can do by analyzing agents with public budgets equal to their expectation. Okay, this is a really, really nice result from a few years back. Okay, so if the agents have independent value and budget, then the optimal mechanism for agents with a public budget equal to its expectation is a 2 times the probability that the budget exceeds its expectation approximation to the optimal mechanism. Okay, so if the budget exceeds the expectation with a constant probability, then the revenue of the optimal mechanism for a public budget agent is a constant approximation to the optimal mechanism for a private budget agent. Okay, so I'm going to start by giving an upper bound on the revenue of the optimal mechanism. And we're going to upper bound it. Again, we're going to look at a couple of cases. So the optimal mechanism, the agent has a random budget. And in the case that the agent's budget is less than the expected value, well, it turns out that we can only get more revenue if we increase the agent's budget. Okay, so in fact, if we take these cases and increase the agent's budget to be their expectation, this gives us more revenue. And so we can upper bound the revenue in this case by the conditional revenue we get from the agent with the public budget equal to its expectation. Okay. In the next case, I'm going to look at the revenue from agents with budget that exceed the expected value of the budget. Okay, and what I'm going to do is say that, well, what is the revenue I'm getting from this per unit budget they have that's over the expected budget? Okay, and I'm going to upper bound the revenue I'm getting optimally by the basically the per unit revenue that we get if I were to if they had that the expected value of the budget. And this is basically a concavity of revenue as a function of the agent's budget. The idea that as the agent has higher budget, they're going to buy higher priced things, which is going to affect our ability to extract revenue from them. Okay, and so again, if we take expectation of the latter case, the expectation of B divided by expectation of B is 1. And so both these two cases were upper bounded by the expected these expected value conditioned on budget being its expectation. Okay, now suppose I run the optimal mechanism for a public budget, E of B, with an agent with a private budget. Well, if it turns out their value is above the expected value of their budget, then they do the same thing as they would before. Okay, they choose the same outcome, we'll get the same revenue. Okay, and so just from this special case, we can say that the private budget revenue is at least the probability that their budget is above the expected budget times the public budget revenue. Okay, and then combining these results, we get the desired approximation bound. Great. So that's the last of the results I wanted to show you. To recap, a lot of economic theory we want to do is analyzing outcomes in economic environments that are complex. The method of approximation helps us understand which aspects of the complex environment are details and which aspects are important. In this work, we were able to take a number of results that are a number of approximation results for single dimensional linear agents and lift those results up to apply to nonlinear agents. And we can conclude from that that, in some sense, nonlinearity is a detail that we don't have to model to understand sort of high order what makes mechanisms good. And this is really nice because we understand linear agents very well, and so we know basically what makes mechanisms good. With that, I'll conclude. Thank you very much for your attention. And I think there are maybe 30 seconds left. We can take additional questions.